Hello all. In the last video, I had discussed the different join strategies which Spark implements and this to decide which physical uh, strategy to use to perform the joins. It's just a quick recap. We have decision starts with checking whether it's an equi join or a non-equi join, and based on that it checks whether there is a hint or not a hint. If there is a hint, it will prefer that particular hint to be used if that hint can be applied. If not, then it will see whether the table which is there is can be broadcasted. If it is there, then it will go to broadcast hash join. If we have the setting where we have in disabled prefer sort merge join, then it will go for shuffle hash join. If not, then it will go for sort merge join. And if anything else doesn't work, then it will just simply do broadcasted nested loop join, which is this part. And if that also is not possible, then it will do a Cartesian product, which is nothing but to map each rows with the other. Same, if it is not an equijoin, like it is just greater than, less than, then we don't have that many options. One is broadcast nested loop join, and the other one is a Cartesian product, and same. It's so this was there. The reason for making another video on this join strategies is we did not discuss how streaming join works. So this was for the batch environment, but Spark also has structured streaming. So in the blog, at the bottom, if you see, we have a few things like a stream to stream join in Spark uses a certain join strategy, which is nothing but join strategy that is used is a symmetric hash join. And how does that work is they has both side of the table basically, and create let's say if we have incoming data from left side of the stream and incoming data from the right side of stream, so they will do the hash of both, keep that hash in the state store, and then the lookup. So one side becomes a probe, one side becomes a lookup. So one side will check whether the key that I have is present in the key in the other side of the hash or not, and same. So that way it does a stream to stream join. And the stream to stream requires a lot of state maintenance, so that is another part. And when it comes to micro batch, like let's say if you have not micro batch, in a sense, if we have enabled for each batch flag in the Spark streaming join, at that time it can choose any join that is present, like it can choose broadcast hash join, sort merge join, shuffle hash join, and or broadcast nested loop join. So for the batch part, because it can do it, it knows the stream is finite, so it knows whether to start and whether to end. So there it does not need uh, any has to be created. I mean, it will follow it. It knows the boundary, so it can create it. It relies simply on the batch join strategy that we have. So this was one part of the video where we discussed that okay, how the streaming join works. Then we also have so these join strategies that we have discussed are based on the fact that they are running on data source v1, data source v1. So Spark has a concept of data source versions like v1 and v2 are there. So v1 was the normal CSV, Parquet, direct file reading, writing, or even the databases. v2 were the sources which works on table formats like iceberg, delta, hoodie. So uh, uh, mm, those are supported via data source v2 API. So in data source v2, if we are looking at iceberg, so we have a concept of storage partition join, which is a join in Spark, which is shuffleless. So when I say shuffleless, it means there will not be a shuffle in this while we are joining two tables which are both on the iceberg platform itself. It's not platform, iceberg format. So let's say we have a table in right side which is also iceberg table, and we have a table on the left side which is also an iceberg table. In those case, in that scenario, in certain cases it can it can actually do a join which does not require any shuffle to happen. So how does that work is, as it's so iceberg table has a concept of bucketing, so which says that we can put with the physical files in certain buckets, and it is similar to high bucketing, but it is when we see in a larger terms, this becomes a superset of that high bucketing approach. What happens is in those storage partition join is, because the files are already sorted and kept based on the buckets, based on the keys or based on the partition strategy that we have followed, we don't need to read from different sources and then shuffle the data. We can directly the physical reading. Let's say, for example, if we require two executors to read, let's say, part one of left side and part two of left side, the same executor on the same nodes can directly look at the physical location and read that. So that avoids certain shuffle. And that's what serverless less join work is. It leverages, as mentioned, it leverages the capabilities of iceberg data. Data is partitioned and stored in a way that aligns with the join keys. Then we can do this with minimal data movement. So this is what happens. There are certain requirements to be fulfilled before we can join. We can use shuffle partition join. So one is that both table must be an iceberg table. Join should be on equijoin. So as I said, it only works on equijoin, not on non-equijoins. And both source and tiles would have the same partitioning strategy. It's same partitioning as a sense it can be a subset, superset, but it doesn't have at least one column should be same. What this is what said that at least one of the partitioning column should be same, and the join condition must include the partition column. It's at least one. It's not that all the columns, but at least one column which is involved in the partitioning should also be part of the join. If there are multiple join columns, at least one of them should be part of this. And also, this is only supported in Iceberg version 1.2.0 and Spark version 3.3.0. So these are the requirements, and there are certain configurations that we have to pass. Sorry, these configurations are all related to how we can. So one is that we disable the prefer sort merge join. Then these two are just for the simulation, that if we want to ensure that okay, we can see storage partition join happening, we disable this adaptive and broadcast. So otherwise it would have simply gone, if the table was small, it will simply go to broadcast join. And which is true, which should be happening if your table, irrespective whether it's an iceberg table or it's an data source v1 table, if broadcast join is possible, that will be the fastest one. So we should, I just this is the config just for making this sure that when we run the code, it uses that SPJ. Now these are is iceberg and clustering, bucketing related some configurations that we have to pass. Only if we have set these things, then only the SPJ works. And there are certain scenarios where SPJs have certain things to do. For example, if we have the partition match, let's say we have monthly partitions and on table A, and table B is also on monthly partitions, and we are joining also on the partition table, its column itself. So what happens, because partitions are same, it doesn't do, it simply matches and the join works fine. Let's say there's a partition mismatch. Let's say we have the same partitioning strategies there, but there are no partitions for, let's say, for the month of March and April in table B, and there is no partition for February in table A. In high bucketing, which relies on the modulo operator, this will not work, because it will say we have mismatch in the number of partitions, so we can't do a bucketing join. But in iceberg or this SPJ, how this is handled is we add empty partitions. So it's basically we are saying that okay, there is a partition which is empty. So anyhow, these columns will not appear in the actual join, but it makes the life easier because we don't have to do the shuffle just to make that thing. So this is one improvement, that we don't have to fix the partition counts in both sides. Then we have, let's say, as I was mentioning, that let's say our table is partitioned on dates, and also it had some certain one more extra column based on which it is partitioned. So let's say this partition and the bucket, let's say we have hierarchical nature where it's a partition is of Jan, and there is one bucket for certain flag, like 0, 1 or 2. So here if we say we have one for the month of Jan, but in this case we have two or three buckets for month of Jan itself. And here it said we have two of for Feb. Here we doesn't have. I think it's only two for. It's a two is also there. So this is one to one match. So that way, see there we have certain buckets which are not uh, in sync. So ideally, if we simply go ahead and try to join, this will require a lot of shuffle, because let's say this data needs to go to this, plus this data needs to go to this. This two also will have to be separate. But how SPJ handles this is because it knows that okay, this partition is there. So this subpartitioning is something which is uh, we can combine, and then what we do is we combine all the buckets which are present on a certain partition. Let's say for example for Jan month on the table A side we had two sub partitions, 0 and 1. So we put that in here and combine them. Similarly for the month of Feb we do combine, and for the March month we only had one. So we do, or one or two, so we can combine. So we are basically combining the sub partitions and then doing the join on the top higher partition, like the bigger partitions which is involved in the column, a join part. So this grouping of input partition based on the join key. So let's say if the join key was on this date, sorry, monthly partition that is happening. So here what we are doing, we group all the sub partitions which were there inside those partitions to make this join work. So this is another improvement that it does, the SPJ does over the high bucketing join. So this is another join strategy that Spark offers. There are certain as I mentioned, there were few cases. So if partitions counts are equal, so it will go ahead with normal. If partition counts are not equal, then it push the empty partitions. If join key is a subset, then it groups the partition based on the join key. And if the join key is a superset of the partition column, then we don't have to worry, because the partition columns are already present in the join key. So there is nothing that we have to do it. It simply works with fine. There is one more where it is used is where we have a skewed, sorry, it is how it handles the skewed partition. So let's say if we have a partitioning strategy in both the sides, the partitions columns are same, but let's say one partition is having very big number of rows. So to avoid OM or skewness in the join, what SPJ does is it will dynamically repartition the larger partition on one side, and it will coalesce smaller partitions into larger ones in one side and then make the equivalent. So it balances that. So it automatically kind of handles the skewed partitions join that will happen. And that's why if you see this partially clustered distribution is the flag that sets this whether this feature will be used or not. So if you see here, we had said this in the beginning that okay, we want partially clustered distribution. So that's how it handles the skewed partition join in SPJ. And the reason why we should be why this is something which was needed though, and which needed a blog, was the fact is this SPJs are very much useful when we are running merge statements in the data lake. So because Iceberg is generally used for the lakehouse solutions, and in lakehouse solutions we generally do an let's say if we are doing CDC, or if we are doing let's say refresh. So we do a lot of times merge update, which is we check first whatever rows are already present and then do a join to making sure that okay, what needs to be deleted, what needs to be added. And that generally involves a join, and that joins can be improved a lot, because we are doing on the same right same table, we are trying to do the join, or let's say we are trying to see whether the rows are existing or not. So the partitioning scheme will remain almost same between the runs of the job. So that's where this storage partition join is very much useful. One or two things that I will like to add is uh, this feature is not fully functional in 3 series of Spark. Actually, it will be fully compatible with 4.0, because there are some features which are still being worked on. There are some issues which are being worked on of this Spark, sorry, storage partition join SPJ. So from 4 onwards, it will be pretty much stable. In 3, it works in certain scenarios and it doesn't in certain scenarios. But again, this is just an improvement. If this is not working, it will fall back to the join strategy that whatever you have defined. So that still works, it still holds good. So yeah, this was one thing that I wanted to add. So to the previous blog. So yeah, this is it. Uh, Thanks for listening and have a nice day.